Greetings A-level chemists, welcome to a little YouTube explainer video explaining why transition metal ions form coloured complexes. And this is a modified exam question, but before we answer it we're going to go through some theory. Okay, so what I've done is I've got the first row of the D block. And remember that scandium and zinc are not transition elements, but they are D block. So what I'm going to do is just choose a transition metal. Let's pick copper, which is a transition metal. And the question says refer to the electronic structure. So let's refer to the electronic structure in SPD notation. Now, the core electrons are going to have the same electron configuration of argon, which is going to be 18. And then we've got our 4s and our 3d. If you prefer, you can do the 3d first and the 4s after. But you've got to remember that it's 4s1, 3d10. Okay? And then if we form a copper 2+ ion, still going to have argon's electron configuration, but we're removing 2 electrons. We're going to remove the 4s first, so this becomes 4s0, and if we remove the second electron that's coming from the 3d, so this becomes 3d9. Okay, so we've got a copper 2+ ion with the following electron configuration. Core electrons have the electron configuration of argon, then we've got 3d9, 4s0. Okay, so we're going to put those in the 3d orbitals, which I can represent as boxes. Okay, so I've got 5 3d orbitals, and each orbital can hold 2 electrons with opposing spin. So I need to put 9 electrons in, so 1, 2, 3, 4, 5, 6, 7, 8, 9. And we stop there, okay? So these are my 3d orbitals. And what I'm going to do, just to explain this, is go a little bit further, okay? I'm going to give these orbitals some labels. So at the moment they're degenerate, they have the same energy. And then what we're going to do is let's give them some labels. So we're going to have a look over here. And what we can see is we've got dxy, dxz, and dyz. Okay, you don't need to know this, but it's really useful for visualizing what's going on. Okay, so let's just have a look at the dxy. And what we can see is that these orbitals, even in the dyz, if that's y and that's z, we can see that the lobes of the orbitals don't lie on the y or z axes. They actually lie in between. Okay, remember that's the region where we're likely to find the electron, okay? And that lies in between the y and z axes in this case. If we have a look on the other side, the dz squared and the dx squared minus y squared, well, these orbitals lie on the z-axis. Okay, that's really important because let's say the complex we're looking at is copper, hexaaqua copper 2+. My ligand in question here is water. So water comes along. And remember, a ligand has lone pairs of electrons. So 6 water ligands come along, and they're going to interact with the electrons in the transition metal center. First of all, they're going to be attracted to the transition metal center, to the charge. So there's going to be attraction, they bond, they form dative covalent bonds, right? Now, what's also going to happen is there's going to be electron-electron repulsion. Electrons are negative, and you've got negative electrons in the ligand and in the transition metal center. So we're going to get a repulsive effect as well. So what happens? Now, not all of the 3d orbitals are equally repelled. So they start by having equal energy. But let's give these guys a label. So let's say that these are dxy, dyz, and dxz. And then these guys are dx squared minus y squared, and this is my dz squared. Okay, just for sake of argument. And then what happens is when the ligands bond, have a look. Which orbitals are going to be repelled more and which orbitals are going to be repelled least from the electrons in the ligand and the electrons in the transition metal center? Well, these guys where the orbitals lie in between the axes in an octahedral complex, these guys are going to be repelled least, okay? Because what I'll do is I will try and draw an octahedral complex superimposed, okay? So there is my water ligand, and there is my water ligand. You can see that the ligand lies on these axes, okay? Hard to kind of show, but you should be able to see that. So the ligands that lie in between the XYZ axes, they get repelled the least. Okay, so we don't get degenerate orbitals anymore, we get this split during bonding, okay? So 3 d orbitals go below and these get stabilized, these are lower in energy. Lower repulsion between the electrons and the electrons in the transition metal center. And then these 2 sets of orbitals, they get pushed higher up in energy because there's more repulsion between the transition metal center electrons and the ligand electrons. These go higher in energy. Higher repulsion. Okay, and that's kind of it. That's pretty much why this happens, okay? For octahedral complexes, we get this split, 3 down, 2 above. Okay, so these are going to be my XY, my YZ, and my DXZ, and these are going to be my X squared minus Y squared, DZ squared. For visual reference, okay? Helps us visualize what's going on. So let's populate these orbitals with the electrons from the transition metal center. So we've got 9 to put in. We're going to start by populating the lower energy orbitals first. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. This splitting, so this distance here, actually corresponds to visible light in copper 2+. So this splitting corresponds to an energy gap which corresponds to visible light. So this difference in energy corresponds to visible light frequencies. So what happens is, now we're getting to the answer. So what happens is wavelengths of visible light of certain frequencies come along. So I'm going to draw a wave, they come along. So this is representing a wavelength of visible light. So certain frequency of visible light comes in, smacks the lower energy electrons, and then what happens is we get a DD transition, okay? So we get absorption. So we get absorption of visible light, and then one of these electrons gets promoted into a higher energy orbital. So it gets excited, and then it moves up. So now that electron is here, and I guess we have a hole there. Okay, so it's been promoted, been excited. It's now in an excited state. Okay, so it absorbs light of a certain frequency, which corresponds to visible light. It gets promoted or excited into an unfilled d orbital. And then what do we actually see? Well, the complementary colors not absorbed are transmitted or reflected into our eyes. So this black wave is representing the complementary colors that we see. And actually, I should have done, for copper 2+, what color should I have used? I should have used blue or cyan. That is the color that we see because copper 2+ complexes are characteristically blue. So they absorb reddish yellow. The complementary colors that aren't absorbed are transmitted or reflected into our eyes. Okay, so let's put all of that into practice. How are we going to answer this question? Well, marking point number 1, we're going to say that they absorb. We can say wavelengths or frequencies. They absorb certain frequencies. Of visible light. An electron is promoted from a lower energy d orbital to a higher energy d orbital. You could just say a DD transition and it gets excited or promoted. The complementary colors, and I'm going to say in brackets not absorbed, for electron promotion are transmitted or reflected into our eyes. And there you go, 3 marks with a bit of theory as well. Ta-ta.